Hey everybody. So we're going to start out in this video talking about arc length, and then we're going to develop a couple other, let's say, geometric ideas about our space curves, right? So we've been talking a lot about vector functions and the associated space curves. So I'm going to start by thinking back a little bit. When a few videos back now, a few weeks back, we looked at parametric equations in 2 dimensions. So maybe something like pair of equations x of t, y of t for some interval of t, right? And this would define some kind of curve in 2 dimensions. And what we figured out was that we could determine the length of this curve by integrating over the interval the following. We take the square root of x prime of t squared plus y prime of t squared dt. Okay, this was our arc length function. Okay, I'm not going to go through the whole derivation again, but it works out from a pretty geometric idea, looking at these little changes in x and y. We can make little triangles whose hypotenuses are approximating our curves, and then this is recognizably the Pythagorean theorem, and we get this arc length formula. Well, we can do the same thing now, or a similar thing in 3 dimensions. If I've got a vector function, r of t, that will have 3 component functions. Same thing, we'll have a little interval. If you remember when we derived the distance formula in 3 dimensions, it looks very much like the distance formula in 2 dimensions. And this is kind of based on the same principle. And so what ends up happening is when we have the arc length in 3 dimensions, it's going to look almost exactly the same. We just have to add, I'm going to use a little bit different notation just to make it easier to write. So instead of just doing our 2 component functions, we now have 3. We get our 1/2 power dt. Okay. So that is our arc length function, right? Remember, this is the vector function r of t, but there's an associated space curve whose parametric equations are the same as the component functions here, and this will give us the length of this curve. One nice thing with all the work that we've done, we have a much more compact way to write this. If you notice what this integrand is, the sum of the squares of the derivatives of the component functions, and then the square root of that, so the square root of the sum of the squares of the derivatives of the component functions, that is simply the magnitude of the derivative of r, right? So this is exactly the same formula, it's just written in a much more compact form, okay? So for example, let's do an example of this. Let's say I have the function r of t is equal to 2t, t squared, and 1/3 t cubed. And let's say it's over the interval 0 to 1, right? So I don't know exactly what this thing looks like, but suffice it to say, there's some space curve that this defines, and from 0 to 1, right, will be some length of it, and this should compute, we're going to compute the length of that arc. So what do we need? Well, we need the derivative of r. We get 2t and t squared. We need the magnitude of the derivative. So I take each of these component functions and square them. So I'll get 4 plus 4t squared plus t to the 4th, and then I need to take the square root of all of this. However, this looks conveniently like a perfect square, right? So factoring the argument of this radical, I get t squared plus 2 squared, and I'm taking it, the square root of it. So now the magnitude of the derivative is just t squared plus 2. So the length is going to be, let's see, our interval was 0 to 1. We're integrating over the magnitude of the derivative, which we just determined to be t squared plus 2 dt. And then this is a pretty simple antiderivative to take. And so we end up with 1/3 plus 2 or 7/3. Okay, so the length of whatever this curve looks like from 0 to 1 is given by the value 7/3. Okay, so far so good. Now here's an interesting little tidbit, or maybe let's say here's an interesting little thought to consider. Suppose I created a different vector function. I'm going to call it I'll call it P, and I'll use P of U, and I'm going to do U to the 1/2, U over 4, and 1 over 24 U to the 3/2, and I'm going to take this over the interval U goes from 0 to 4. Okay. Well, if you inspect this carefully, what you will see is that this is in fact describing the same set of points. P of U and R of T describe the exact same set of points. In other words, they spit out the same vectors. They just don't spit them out for the same vectors, the same values of T and U, right? So for instance, when U equals 0 and T equals 0, both of these start at the origin, right? Or the 0 vector. By the time T gets to 1, right, it's pretty simple to compute this. We're at the point 2, 1, 1/3. Well, if you plug in U equals 4, we're at that same point, 2, 1, 1/3, right? And so it just takes a different amount of time. In this case, U is taking longer. If we think of our input as time, it's taking it a bit longer, but it's describing the same set of points. The relationship between these two is just that U equals, what is it, 4t squared gets you this relationship, right? So it's just a different, what we call this is a different parameterization of the same curve, right? So a curve can have many, many, many parameterizations, right? The easiest way to think about it, I think, is imagining particles moving. So one particle could, for instance, move between 2 points along some curve at a steady pace. One could go really fast in the beginning and slow down. One could intermittently stop. You know, there's all different kinds of ways you could travel between 2 points along the same path. It shouldn't change. It shouldn't change the arc length to have a different parameterization, and it doesn't. I'm going to leave that for you to check for yourself with this parameterization. See if you can compute what we just did only using what we have here, and see that you get the same length. And it can be shown that the length is independent, meaning it won't change with different parameterizations, right? Which it should be, right? It doesn't matter how fast you drive, the distance down I-5 from Seattle to Portland should be the same, right? Regardless of how fast you drive. It just will, you can change how long it takes you to get there. So this idea that length is like an intrinsic property, a geometric property of the curve, separate from the particular parameterization we use, is going to be important to us. So let's do something a little more with this, and we'll kind of build towards something. One thing we can do, we can create an arc length function. Okay. So given an r of t, we can create the function s of t. Let's say r of t goes from the interval alpha to beta again. We can create a function which is an integral from s from alpha to t of r prime. Now I'm going to use u here just to mean a dummy variable, du, right? So again, this is just a function. If you input a value of t, it gives you a bound, an upper bound on your integral. You already have a lower bound. You integrate just like we did and you get a length. So this is spitting out the length at different values of t, right? So this is an arc length function. S of t is the arc length, okay? What happens if we take the derivative, ds dt? Well, our fundamental theorem of calculus tells us that we have the magnitude of the derivative, right? Well, let's think about what this is telling us. This is how does length change as time changes? In other words, this is the speed, okay? This is the speed of our function, right? Which also helps us understand or see a little more clearly that r prime is like the velocity. It's the speed with the direction intact. Here we've removed the direction by taking the magnitude. We're left with just the speed, right? So we mean two different things by speed and velocity. Velocity includes direction with the magnitude information, whereas speed just gives us the magnitude, okay? This function is going to be important, although we don't often see it directly in this course, but what we're going to use it for is to get a neutral parameterization, okay? So for instance, imagine driving down a road, right? And you're trying to describe how tight a turn is, okay? Well, if you're in a car driving and you're going very, very fast, the turn feels tighter. You'll feel that force. You'll feel yourself being moved by the turn, as opposed to somebody in a car traveling very slow, right? But the curve itself hasn't changed. In other words, the speed at which we're experiencing a curve can change our notion of it, right? The same curve can feel very differently. We don't want that if we're trying to describe geometric properties of the curve itself, right? So maybe a better way to measure something like the curve would just be how much does the direction change given the length? Forgetting about the time information, that's what speed has in it. We can just think about the length and how we change relative to how much length has passed. So how does our direction change as length of curve has changed? So with that in mind, we're going to define something called curvature. Okay, sorry for a second. I lost my spot for just a second here. Oh yeah, let me do one thing before curvature. So one thing we can do is we can reparameterize something with respect to arc length. So let's do an example to see exactly what I mean. Okay, r of t is going to be sine of t, cosine of t, t. Okay, so all I'm going to do first is I'm going to find this arc length function, and then we'll see what we're going to do it. So r prime is cosine t, negative sine t, and 1. The magnitude of r prime is going to be, oops, we're going to square each of these component functions and add them together. So I'm going to get cosine squared t. When we square the negative, we'll get rid of it. Sine squared t plus 1, taking the square root. Well, we know what cosine squared plus sine squared is 1, so we've got 1 plus 1, or 2 to the 1/2, and I'll use root 2 for my notation. This is our magnitude, okay? So now, let's make some more space. Let's do this. So now, let's create this arc length function. We have all the pieces we need. So S of t is going to be, oh, sorry, I forgot to give us an interval. Let's just say it's from we'll just keep it open-ended and say t is greater than or equal to 0. So let's create an arc length function from 0 to t. Remember what we're putting in, r prime of u. Well, our r prime, the magnitude of r prime is just root 2. So our function in here is just root 2 du. And we can actually take this integral pretty straightforward. It's going to be root 2u from 0 to t, or root 2t, okay? In other words, s is equal to root 2 times t, okay? That's our arc length function. For each unit of time of this parameterization, we get the square root of 2 units of distance, right? So if 1 second passes, we'll get the square root of 2 centimeters or whatever units we're in, right? So we're getting a little more length per unit time than a unit length, right? So what we can do with this, I can take this equation and solve it for t and get t is equal to s over the square root of 2, okay? Watch what this does. So I'm going to now take my function r of t, and I'm going to use this new function. I've taken t and made it a function of s. So I'm putting t of s into r of t. What does that look like? We get sine of s over root 2, cosine of s over root 2, and s over root 2. Let's take the derivative, right? S is now our variable. We're taking a derivative with respect to s and get, let's just write it this way. I think I have too many parentheses in there. I'm going to leave it. We get, what happens? We get, well, we get the cosine of s over the square root of 2, and we also get a chain rule popping out, a 1 over the square root of 2. We'll get a negative 1 over square root of 2 sine s over the square root of 2, and we'll get 1 over the square root of 2. Okay. Now let's take the magnitude. I'm gonna change my notation here a little bit. Just say this is the derivative with respect to s of r. And what happens? We square each of these things, right? So when I square this, 1 over root 2 squared gives me 1/2, and then I have cosine squared s over root 2, plus 1/2 sine squared s over root 2, plus 1 over root 2 squared, which gives me 1/2. We can factor 1/2 out of the cosine and sine squared, which means we get 1/2 times cosine squared plus sine squared, which is 1. So it looks like we have 1/2 plus 1/2. The square root of 1 is 1. So when we reparameterized this, so what this is called is we're reparameterizing our curve with respect to arc length, meaning we take this arc length function, find the inverse, and use that as our new variable. We get a new parameterization for the same curve where the magnitude of the velocity vector is 1. In other words, the speed is 1. For each unit of time that passes, 1 unit of length is gained, right? So if I'm in miles per hour, it's like going 1 miles per hour. And so it gives us this neutral parameterization, so we can eliminate that problem I described of, for instance, trying to measure a curve without eliminating the speed. The person going 60 miles per hour would measure that curve as a much stronger curve than the person going 2 miles an hour, right? If we measure everything from the neutral position of one unit of length per 1 unit of time, we get a standard measure that ignores the speed that something is going, okay? So that's the big idea with this. Now, in practice, I set this function up to make it easy to solve t as a function of s, right? This thing we did down here, this is not typically easy to do, okay? It's very convenient that my arc length function turned out to be such a simple function. So we aren't typically able to do that. However, it doesn't mean that this is useless, because we can still use this idea to derive some measures that don't let length sort of confuse our information. So let me try to make that a little clearer. We're going to do something called, or develop something called, curvature. Okay, so what we want to do, so let's do a little quick drawing. If I have a curve, I want to measure, remember we had a vector function we called the unit tangent vector, which is r prime of t divided by the magnitude of r prime of t. What this is a function that spits out vectors along some curve where each one is a unit in length. Right? So pretend these are all exactly 1 unit in length. That's what this vector function is, the t, our unit tangent function, is spitting out. Okay? So imagine these little vectors along this curve in the tangent direction, but they're all 1 unit in length. What we want to measure with curvature is, how does the direction change as the length changes, right? If you had a path that went like this, right? There's no curve to it. Our direction barely changes. As we gain length, as we move along this curve, those arrows are in almost the same direction, right? They're just changing ever so slightly. On the other hand, if we have a curve like this, and I do the same game, right? I'm starting out facing this way, and very quickly, right, in less length than was up here, my vector has turned around completely, okay? So in a short time, we've changed a lot, right? So what we want to measure, what we're going to call curvature, this is another Greek letter kappa, I think, is the magnitude of the change in the unit tangent vector divided by the change in arc length. Okay, how does this unit tangent vector change per unit of length changing, right? So just from this picture, what you should be seeing or maybe absorbing intuitively is, if this direction doesn't change much, we have low curvature. If the direction changes a lot in a short period of time, we have high curvature, right? You can think of a big circle versus a small circle, right? If you imagine spinning around these circles, even if you're going at the same linear speed, in this big circle, you're barely going to notice it because it takes you a long time to change direction. Whereas in this tiny circle, you have to change direction very quickly relative to how far you've traveled in linear distance. However, this is tough because then we need our unit tangent vector to be a function of s, which I just explained was very difficult to do in most cases, right? Our example was one that was set up to be easy. But if you try to do this in practice, it's often very, very difficult, if not impossible. We're not out of luck, though. Notice, if t were a function of, if we use the chain rule and take the derivative of our unit tangent vector with respect to t, we get this, right? Where s is a function of t, so you're using the chain rule here, okay? Well, what does that mean? dt ds, we can solve for that. dt ds is equal to dt dt over ds dt, right? I'm just moving this part of the derivative to the other side, which means curvature can now be expressed in the following way. we're taking the magnitude of what I have down here, dt, dt. Keep in mind, these are two different t's. The capital T is we're taking, how does the unit tangent vector change with respect to time, divided by how does the arc length change with respect to time. Well, what is this formula really saying? dt dt is just our regular derivative of the unit tangent vector. ds dt, if you recall from a few moments ago, is the magnitude of the magnitude of the derivative of our vector function, right? Remember when we created s of t, it looked like this. And so ds dt was just r prime of t by the fundamental theorem of calculus. And so this now, let's just write it once with no other pieces in the way. This now gives us a pretty compact formula for curvature. And this is a measure of the tightness of a curve that doesn't depend on the particular parameterization. For all parameterizations, you'll end up with the same measure, right? And we want that. It's a geometric property of these curves, right? It doesn't change how fast this curve doesn't change how fast how much of a curve it is because I go through it faster or slower. Okay, let's do one example with that to finish this video. So I'm going to get rid of all this. Let's keep this formula up and get rid of all this. Okay. So let's do one in 2 dimensions because this gives us some good intuition. Let's say I have a parameterization of a circle. We've seen this before. A sine of t. So this is a circle with radius a. A is some constant in this case, okay? So I'll just say again, t is greater than or equal to 0. R prime of t, oops, I don't want that. So I'm gonna go ahead and compute the curvature of this thing. And so I need r prime, I need t prime, so I have to do a bit of work first. R prime of t is negative a sine of t, a cosine of t. Okay. The magnitude of r prime of t is going to be the square root of a squared sine squared t plus a squared cosine squared t, which is just a after a little bit of algebra. Okay. Now we want to compute t of t, which remember is r prime of t over the magnitude of r prime of t, the unit tangent vector. So I'm just dividing r prime of t by the magnitude of r prime, which is just a. So it's just going to be dividing a out of these two components. So it looks like negative sine t cosine t. Okay. All right. It's easy to see that this is a unit vector. Okay. We also need now t prime. So let's take that derivative. T prime of t is equal to negative cosine of t, negative sine of t. Okay. So let's see if I've got everything I need. We've got, oh, and then, so now to compute curvature, sorry, I was forgetting one step. I need to take the magnitude of t prime over r prime. So let's compute t prime of t over r prime of t. This is going to be, sorry, we need to compute this and this. So what do we get for the magnitude of t prime? It's going to be cosine squared t plus sine squared t, the square root of that. We've already computed the magnitude of r prime is a, and we see that the top is just 1. Okay. So that's the curvature. We have to go through all these steps, pick up all these pieces. right? None of them are particularly hard, but it can get a bit ugly in taking these derivatives and divisions and so forth. But this particular example gives us a nice understanding of what this curvature stuff tells us. Notice what happens. So remember what this parameterization, we were measuring the curvature of a circle, radius A, right? So here's a particular circle. If the circle gets bigger, the curvature gets smaller because A is our radius. If the circle gets bigger, we're getting a larger and larger denominator. We're getting a curvature closer and closer to 0, right? If I make this circle bigger, look at what's happening to those curves, right? We don't notice, for instance, when we travel around the Earth that we're curving. It's such a wide circle that it appears flat where we're at. On the other hand, if you make a very small circle, you're going to be turning very, very, very tightly, right? So again, this is equivalent to driving in a car and going around a long mountain pass with a slow bend to it. You hardly notice that you're turning. Whereas if you take a tight corner, right, around a block or something like that, you feel that push to the outside. So that's another way to think of what curvature is telling us is, right, the tighter the curve, the bigger the number gets, the looser the curve, the smaller the number gets, and we can see it in the geometry of a circle. Okay, let me leave you with one last thing, an alternative formula for the curvature. I am not going to derive it. It's doable and easily findable, but I'm just going to leave it as an option. It looks worse, but in practice, it is often an easier thing to compute. It turns out you can compute the curvature by taking the cross product of the first and second derivative of the vector function and dividing it by the magnitude of the derivative cubed, right? Which again looks way uglier than this thing here, but right, I took an example here where taking derivatives was relatively easy. We have to take a lot of derivatives here. There ends up being a lot of quotients and things like that, and so they can get pretty ugly pretty quickly, whereas this one can sometimes stay a little bit nicer. But let's leave it there with the idea of curvature. Thanks everybody, and I will see you all next time.